Okay, so good afternoon. So we can start. So we had talked about products, and in particular we introduced the Sega embedding. What? I didn't understand.
Camera is going for record. It means
Yes.
Yeah, I already pressed the button. Thank you very much. It's no, it doesn't matter. One says it once, so okay. Anyway, so it does work. Okay, this is the embedding. This is sigma embedding of the n times pm. So n okay, which was just given by taking the point here, this homogeneous coordinate a0 to n, point here, and we map this to the tuple of all possible products. Okay, this was this map. We had seen that this is well defined, it is injective, and the image is a closed subset. In Pn is a risky closed subset. And we will, as I said, often want to identify sigma, the enthalpy and with its image. So that this closed subset is called, we denoted by Z. Okay, so this is more or less where we work. Now I want to say something about that we have an open cover by defined sets, like in some like we have for the n itself. So we know that the n has open cover, which was given by open subset ui, which is the set of all E0 to an, where ai is not 0, and we have the map ui, this not the other way around, I think, from en to ui is an isomorphism. In the same way, this is now the factor Pn, we have this. On the factor Pm, obviously we have corresponding, open subsets. So say Pm has an open cover by, say, I call the open subsets Uj. The coordinates here denote E0 Pm, such that Dj is different from 0. So this is maybe a little bit of abuse of notation, because I write, it could be that I is equal to j, these are still different sets, but I mean, just when I write j, I mean I am on Pm, and when I write I mean I'm on Pn. So I think you can handle that. Okay, and so therefore P large n, there the coordinates were, aij's, so has an open cover by some open subsets uij, which is the set of all A, say KL where AIG is different from 0. And obviously, so again we could have then Uij from A and so Uij is a nice one. The same thing, it's always projective space, we have this covered. Okay, so we want to see that somehow this is compatible with the Sega embedding. Embedding. So what does it mean? So I can, for instance, take the map sigma ij from the n plus the m, which is just the n times the m, we map here with we map this to Uij by sending a point P, Q to the sigma of I of P Uj of Q. So in other words, so we have here En times Em. We map this in some sense with Ui times Uj into Pn times Pm, and then we apply the Sega embedding. And okay, so this is the map, and we can see that if here we start here, so we go first. This will be mapping into Ui times Uj. So here the ith coordinate is not 0. Here the j's coordinate is not 0. So here the Uij's coordinate will be non-zero. So we get into this open subset. So on that end, so what do we see by definition? Now, if we look at the image, we take sigma intersected Uij. What is it? This is the set of all points in this Uij. So we have A, K, and L. Such that this now lies in sigma, so it means the coordinates of the points are products, no? One point in projective space here, one here, such that AI sigma, such that AI times Pj is different from 0. So this is just the same as the image of so the set of all images sigma from A0 to n B0 Bn such that A0 to n is in I into 0 n, so this was n in Uj. This is just equal to sigma of I times Uj. So we see that the intersection with this chart of this big projective space is just the image of the product of these charts, so which shows that things are really compatible with each other. So everything works as it should. And now we want to see that if we use this map, it actually is an isomorphism onto its image. So we have here this map, sigma ij from In plus M to Uij. Obviously it cannot be an isomorphism to here because this is much bigger, but it is an isomorphism to here. Sigma intersect Uij. So this is the open subset in sigma, so this makes sense, is an isomer. So it means that, okay. Let me just see. So for obviously for all INJ. Obviously, it doesn't depend which INJ I chose. The argument will always be the same, so I can choose for simplicity that I is equal to 0, j is equal to 0. So, how could I write, and then it's kind of, so if I take sigma 0, 0, so what does it do? I mean, I first maybe write it here, so if I apply to an element in AN, which is A1 to AN is the first part, then B1 to Bm is the second factor. What is it? So I first embed it into projective space, so that means I add a 1 and make it a vector projective space. And then I consider the class which is obtained by taking all possible products. So this will be an element in this projective space P large N, Cij, I from 0 to N, J from 0 to M, with the following. So C 0, 0 is equal to 1, because it's the 0 here times 0 here. C I 0 is equal to AI, and C 0I 0J is equal to HJ, no, for all INJ, and so for INJ bigger than 0, and finally Cij for INJ bigger than 0 is equal to AI times EJ. This is the definition that we gave. Because it's, as I said, the coordinates are just the product of the corresponding coordinates here in projective space. But you have first add the 1 here and the 1 here, so as the 0th one, and so in this case we just get the corresponding factor. So, okay, so this is the thing. So this also means you can see this is now a morphism. Because the coordinates of the map are regular functions. 1 is a regular function. So in particular, so these are all regular functions. They don't all vanish at the same time, because they can't vanish at the first time, because this one is 1. This is a regular function because it's just the ith coordinate. So it's just, so as a function, it is just xi. Here, this is y, as a function is yj. This is xi times yj. So these are all regular. And so this is homomorphism. Okay, and so now I can look at the inverse morphism. So I want to have the inverse map. I want to see its automorphism, and I just say, if I call the coordinates on this large Pn, this Zij, then this is just given by, say, Z10 divided by Z00, Z until Zn0 divided by Z00, and then Z01 divided by Z00 until Z0n divided by Z0. Because if you are in the image of the map, so you want to show that if we are on sigma type intersected with this means in the image of the map, then this is the inverse map, which then gives us back E0 to n. But in this case, Z00 is 1, so this thing is not there. So you can see first that these are all rational functions on this thing, and you can also see the denominator never vanishes on this image because Z00 on this image can be chosen to be 1. And they also have no common zeros on well, no, here we are. This is all we need. We are defining a map to a fine space. So what we need is that these are regular functions, that's all. And so certainly these are regular functions because they are rational functions, the denominator is nowhere 0. We are defining a morphism here from sigma to an plus m. And for this, we need an n plus m tuple of regular functions, and here it is. Okay, and you can see that this map is the inverse of the previous map, because this will just be, if we are in the image, this will just be A1 until AN, and B1 until Bn. And you can also see the other composition. Okay, so this is kind of trivial, but you see, this thing is actually equal to the image, so you see that also if I view Pn times Pm as the image, so if I identify sigma with Pn times Pm, then it has again a cover by affine spaces, which are just the product of defined spaces which cover An and Bn, as it should be, and everything is compatible. So let me write this down. We're not using that so much in the future, but somehow it does. If we identify sigma in Pn with the Pn times Pm via sigma of PQ is identified with PQ, then we see that, so this open cover by affine spaces here of Pn times Pm is just the product of the what we had before. So then we just have the open cover and the n times Pm by the ui and Cj, which are just would just be the images of An times m after sigma ij. So I equals 0 and j equals 0 m, which are isomorphic to An plus m. So could say And so in this identification, this map here, which we have here, so sigma ij have this map sigma ij from an plus m to sigma intersected uij is just the map pq. It's just the map is just becomes just ui times uj. No, pq is mapped to ui of uj, because that's precisely how I had defined. I wiped it out, but sigma ij was just first you take this and then you compose it with sigma, and with the inverse is pi times pj, where pi was inverse of ui and pj one of the other one, from ui times uj to a. Okay. So maybe we're not. I think in the notes I used this quite a lot. Maybe this time I will not use it so much. But anyway, you can just see we have this cover. Everything. So if so every product of varieties has naturally. So in particular, so Pn times Pm has naturally this cover by these affine spaces, and so this would also hold for subvarieties. So now we also. So until now we have talked only about Pn, the product of Pn and Pm. Now we're interested in the product of projective or quasi-projective varieties. So we have to see that if x in Pn is closed and y in Pm is closed, then x times y is closed in Pn times Pm, or with this identification that so that sigma of it is closed in sigma. Okay, so let me do this. Yeah, sometimes it would in some sense be easier if I could work with the abstract varieties and just say Pn times Pm is Pn times Pm and I'm not identified with this. But there is some difficulties in doing that, and I somehow, I don't know, maybe you are smarter than the students were a few years ago when I tried it, and I had to give up because after I explained it all, nobody understood anything, and then I had to start again the course. And so I prefer maybe to do it like this. But it's not so. Anyway. Okay. So just so if x in Pn and y in Pm are closed subvarieties, then x times y is a closed subvariety in Pn times Pm, which with our identification means sigma of x times y is a closed subvariety of sigma, well maybe I write sigma of Pn times Pm, which itself is a closed subvariety of Pn. So therefore it means the same as saying that sigma of x times y is a closed subvariety of Pn, because closed and closed is closed. So I will just formulate this as an exercise.
Sigma of x equals y. X equals y here is a theoretical product, or?
Yeah. Yeah. Here I'm just taking the set theoretical product. So this is in Pn times Pm. So basically, yeah, the identification is that sigma is identified to be the identity. So I pretend that sigma is the identity, but here x times y. So one could say that this is the so here by x times y I mean the set theoretic product. By here I mean the image in Pn times Pm, which is a kind of which we want to see as the categorical product. I mean in the sense of fulfilling the universal property. So exercise. But I mean, I more and more want to somehow stop distinguishing between the two, because it's much more useful to think of this thing as I mean, to think of the product as like it was the set theoretical product. So you could somehow think that somehow you have transported the structure of the variety to this somehow via pulling it back via the Seg embedding. That would be more natural. You know, that you say a function is regular if it is, if the composition is regular, a map from this thing to anywhere, or is a morphism if the corresponding composition with the same embedding one way or the other is regular. But I would stick to this. Okay, so the exercise is the following: if x is a zero set of some polynomials where the gi are some polynomials including 0 to xn, so this is the n, and y is a zero set of, say, h1 to ht, m, where the hj are some polynomials in, say, the values here equal y0 to ym. Then I claim if I take sigma of x times y can be written as first I take sigma, so the image of Pn times Pm, intersected the zero set of, I write here gi of z0k until z nk times hj times c L0 until z Lm, where I and j, where I and j, k and l run through all possibilities. So I equals 0 to s, j equals 0 to t, k equals 0 to m, l equals 0 to n. So you take just all possible products of elements from here to here. This is also, we saw in the fine case, that the zero set of the product of two ideals, I mean, if you take the zero set of the product of two sets, then that's the product. So where the product of two sets is just all possible products of the things, just gives you the product of the zero set, so that seems reasonable here. But we also have this thing that we choose all possibilities how we take these coordinates here, which just means we make sure that, so you can maybe, you see that in some sense, so the coordinates here would be ai times bj, and if we take all possibilities, then somehow this will, the extra coordinate will cancel out. You can work it out. It's quite simple to see that this is the answer. And so this will show that this is a closed subset in sigma, so which in this statement would translate into saying that if x is closed in y, in Pn, y is closed in Pm, then in this sense, x times y is closed in Pn times Pm. So here I've just, the exercise just shows it's a closed subset. Now we want to show it's a variety if x and y are varieties. So irreducible. That's the same statement as in the same proof also as in the defined case. We see. So, I actually need it. Yeah, position. So, if again, as before, if we identify n times Pm with sigma of Pn times Pn via sigma, then the claim is that the two projections are morphisms. You want that the projections to the two vectors should be morphisms. And the second statement is that if I take sigma of Pn times Pm, now in mode I don't do the, is irreducible. And if x in Pn and y in Pn are irreducible, then sigma of x times y in Pn is irreducible. So if you make again this identification as before, it says that if x and y are irreducible, then x times y is irreducible, like in the appendix. So I claim, so for one, obviously, I only need to show it for the first projection, because it's the same. So obviously, this means that I take the inverse of the Sega embedding as a map. So what this really means, I take sigma to the minus 1. So I take P1 composed with sigma to the minus 1. From sigma to the n, we have to show that this is a morphism. No, because that's what's meant by this thing. And so I just claim that P1 composed with sigma to the minus 1, this is just, can be written as Z0j divided by Zij until Znj divided by Zij for any ij in so any I from 0 to n, j from 0 to n. So I claim I can write this map So this morphism I can write like this in these in many different ways, like this. So first, this means it's a morphism because, as you can see, these are rational functions. So this makes it a rational map, and so the denominator you can. So if you choose the I and j properly, you can make sure that for any point you can find something where this is not 0. And you can also make sure that these have no common zeros. Just think of it. If you have the image, you can. So this will be defined everywhere. So this implies that E1 composed with equal to -1 is a rational map. Defined on the whole of something. No, for different parts of so each of these, basically each of these, for each ij, it will work on uij. So if you fix I and j, then this will be a morphism on the open set uij, and the uij cover sigma. Okay, now we have to know, maybe one should now see that this is true. I mean, that this is always the same. So what we have to see is, so first, so a morphism or a rational map is given by an equivalence class of tuples of rational functions. So we have to see that these all lie in the same equivalence class. No? We cannot randomly write down something. So that means that we can, for different values of I and j, this is always the same rational map. So to change, say, I to k in this expression, so if I want to have, so the same thing where I is now another value, k between 0 and n, we just multiply by what is it? By Cij divided by Ckj. No? Then I just, this becomes in the numerator nothing is. I just multiply with this thing. So this thing it cancels, and in the denominator we have this. So this is, so obviously equivalence class, the equivalence relation is by multiplying by a rational function. This is rational function, so if I multiply the whole thing by this, I get the same equivalence. And to change, what was it, j to some other element L, it's a bit more complicated. We have to look at where we are. That we are on sigma, which is the zero set of this set of polynomials, so that there are certain identities. So we use that on sigma we have what was it? Cij times C. I have to make sure I don't make, yeah, times C L is equal to Cil times C Kj. No, this was for all I and j. And so Ckl divided by Cil is equal to Ckj divided by Cij. I got this right? But I wanted to, so for any, so it just means that I can replace the j here everywhere by L, because this actually, as a rational function, these two are equal, no? on this, and so I can just replace everywhere L, j by L, no? Because of this identity. No? So I mean, in S of sigma we have this identity. No? So therefore this. Okay, and so therefore in the fraction. Okay, and so this means it is indeed a morphism defined everywhere. And now we come to the second part. So here we just do the same proof as in the affine case. We have to see that what was the statement that the embedding of one factor as p times as the image of p times y or q times x, that this is a continuous map. This was what we used to show that it was irreducible, and so we want to see this here also in the same way as before, namely by saying that's a morphism. So, let q equal to p0 to Pm be a point in Pm. Then the map IQ from Pn to sigma, which is sigma of n times Pm, which sends a point P to sigma of PQ. This map is what? Is the polynomial map. I could just say it's given by B J times xi, I from 0 to n, j from 0 to n. After all, it's just, you send something, you send to all possible products. And so this is a polynomial map, therefore it defines the morphism. Thus the morphism thus continues. In the risk topology. So therefore, by the lemma, if we make this identification, we see that, so and obviously the same holds for JP from y to sigma q maps to sigma of CQ. So for all these, we have the same. This is also a morphism by a similar formula, and therefore continuous. And so by our lemma, we know that if we have a topology such that these maps are continuous, then the product is irreducible. So by lemma, we have that is irreducible. And obviously, if x are subvarieties, then we have these corresponding maps are still morphisms as restrictions of morphisms. I could have done this immediately, so IQ and JP are morphisms for all P in N, Q, no, Q in X, Q Y, thus by the same argument sigma of X times Y is irreducible. No, because the statement was that if I have two irreducible topological spaces such that the topology on the product has the property that these maps which embed one factor as a slice in the product, that these are always continuous, then the product is irreducible. That we show. Okay, so this was that. Okay, so now we know that. So now I just want to briefly just repeat again our identification also for projective and quasi-projective varieties, and then state and prove the universal property, and then we will deal with let me see. Okay. So product of quasi-projective varieties. So in future, so will, unless it is strictly necessary, no longer kind of usually suppress the sigma and the other sigma, only when it's really necessary to explain what's going on, that we keep track of it, I don't say it. In future, we identify Pn times Pm with sigma of Pn times Pm in Pn, where n was this product. So thus Pn times Pm is a quasi-projective, is a projective variety. If X in Pn, Y in Pm are projective, identify maybe as a quasi-projective. So opens up the projective them identify sigma of X times Y with X, maybe it was the other way around, no. X times Y with sigma of X times Y in Pn, and I haven't completely so we have just seen that if X and Y are projective, then X times Y will be projective, namely closed, and it's not difficult to see if X and Y are quasi-projective, then this will be quasi-projective, so open and closed. So if these are projective varieties, so this means a quasi-projective variety. Which will be projective if X and Y are projective. Both X and Y are projective. And now, so let's just look at one very simple example. So one case where it looks simple, whereas in general, for instance, just the projective space given by this, the product of projective space is just given by the sig embedding looks, if you think of it, looks very terrible. You have extremely many equations in a very big projective space. So we can look at the first non-trivial case, P1 times P1, which lies in P2 times 2 minus 1, so P3. And then it's just a 0 of one polynomial. Doesn't look as terrible. For example, without identification, we have P1 times P1 is equal, strictly speaking, sigma of P1 times P1, or just like this, 0 set of Z00, Z11 minus Z01, Z10. So I claim it's just 0 set of this one equation. If you look at the definition of the equations of which the product is a 0 set, there will be many more. But all the other equations are of the form 0 is equal to 0. So you always have that the terms cancel out and nothing is left. But this is the only one which survives. You can check it. No? So it is therefore it is a hypersurface. So you could see a degree 2 hypersurface in P3. So one can realize P1 times P1 as such a hypersurface. And actually, I think in the notes I have some kind of picture. You can actually see, if you write down such a hypersurface, such a quadratic equation, that this would be covered by 2 sets of lines, which are just the images of a point here times P1, or a point here times P1. And this one can make as an exercise. Easy to see. So show that if I take right side, like sigma of P times P1 and sigma of P1 times Q in P3 are lines in P3. So just the 0 set of 2 linear equations. So you have some kind of picture. I don't know whether I can somehow. Now. So this thing has kind of 2 different families of lines. So I think, how does it go? So if you make some kind of picture, you could think. So. I know I don't. But anyway, so you start with something like this. You have P1 and P1, and now somehow it's embedded in P3, and there still you can see the lines. Although it's now kind of anyway, you can look at the notes. Unfortunately, I can't draw it now. This drawing is actually the real challenge. Okay. And now I wanted to show you the universal property, which kind of justifies calling this image by the sig embedding the product, because it satisfies the universal property of the product, which is the same as before. Following proposition. In future, this is mostly what we use. We don't really have to care about how we have defined the product. So, universal property. So, let x and y be varieties, by which I mean we actually quasi varieties. first, this we have already seen. If I take P1 from x to y times y to x and P2 x times y to y, these are morphisms. And this is, I mean, maybe I should have done it here, but anyway, we already proved it, so these are just restrictions of the corresponding morphisms. From n times n. So it's seen that the projections there are morphisms, so if I restrict, they are still morphisms. Okay, and so then the second statement is that for any variety Z, the morphisms to the product Z to x times y are precisely the pairs FG from Z to x times y, which just, F maps from Z to x, G maps from Z to y. So we have two morphisms for F x, Z to x, and G, Z to y morphism. Yeah. So a morphism, so the product is just the same as a pair of morphisms. One to one factor, one to the other factor, where Fg was, as usual, the following thing. So point P is sent to F of P, G of P. Okay, so we only have to show the second. So so we know that P1 and P2 are morphisms. So we just have, so let say P from semicolon H from Z to X times Y be a morphism. Then in the same way as before, we have that if you have a point and we have an H of P can be written, so first we have that if you put F equal to P1 composed with H, G equal to P2 composed with H, then these are morphisms as compositions of morphisms. One is a morphism to X, one is a morphism to Y, and obviously our morphism H is this thing which we call Fg. And for all P in Z we have H of P. Now it has two components, one in X and one in Y. The component in X is this projection, the component in Y is this. So this is just F of P, G. So H is equal to Fg. Okay, so that's one direction. Conversely, if I have a pair of such morphisms, then I have to see, this gives me a morphism for the product. So if say F from Z to X, G from Z to Y are morphisms, so then we can write f is equal to f0 to fn, where these are some rational function, that's the equivalence classes of these. G is equal to G0, Gm. And then if we apply the Seg, now we use the Seg embedding, so how does one get the product map? Well, according to the Seg embedding, you get the pair is mapped by taking all the products of all the coordinates. So we put H to be the map from Z to a priori to Pn, but then I claim it goes to x times y, so simply speaking, sigma of x times y, which is just given by fi times gj, so I 0 to n, j to m. And this will, if that's a rational map, you can see that this will be also defined everywhere. If this is defined everywhere. So this is a morphism, and we see that and you can check. So actually what I wanted to say is I take fg like this, given in this way. So I claim that the map fg, which the first component is given by this f, so p goes to this, second component is like this, sends point q to g0 of p and the gm of p, that this is given by this. And this follows directly from the definition of the Seg embedding. And this is a morphism because these are. Okay. So this would be this thing. So much for this universal property. Now, so it's just some stupid consequence because we just want to introduce the notation. So as an example, what is so one special case of this is that you can look at the product of two morphisms from the product of two things to the product of two other things. So let f from x to y, and from x, what did I want? Y, and g from c to w, the morphisms. Then I can take the product morphism, so which I denote like this. So f times g means the first maps to the first, the second to the second. So from x times y to x times z to y times w, namely just a map pq is mapped to f of p g of q. This I want to note like this. You have fg is from one thing to the product of two. F times g is from the product of two to the product of two like this. Is a morphism. Well, and this is just because we can write it in terms of this here, namely so this is because I can write f times g as f times composed with p1 G composed with P2. No? So this means I take X times Y, then we have here the first map to the first, was it Y? Yeah, X times Z. So we first, in the first component, we first map to the first factor X, and then we apply F. Here we map to the second factor, and then we apply G. And this is precisely the map I've told you. No? That means F times G of PQ is F of G of P. As we want it. This was a P. And so this is a morphism as a composition of morphisms. This is a morphism as a composition of morphisms. So in particular, if in this case X is isomorphic to Z and Y is isomorphic to W, then X times Z is isomorphic to Y times W. X is isomorphic to Z, Y is W in the forms X times, did I want it like that? Maybe not. X was maybe supposed to be isomorphic to Y, and Z was isomorphic to W, then X times Z is isomorphic to Y times W. No? We just we have this morphism from one to the other, and the inverse morphism, and obviously the composition is better. Okay. Now another thing, we want to know what are the closed subsets of Pn times Pm. So we have to be careful what we mean by that. So if we make the identification of Pn times Pm with the image in large Pn, then the closed subsets of in Pn times Pm are the inverse images under sigma of the closed subsets in P large N. No? So we have, but now we want to after all work with the product itself, not with the image all the time. So we want to describe in terms of this space what these are. And so we want to describe in terms of polynomials what are the closed subsets of Pn times Pm with this identification. It will turn out that these closed subsets are the zero sets of what one could call B-homogeneous polynomials. So on Pn, we have polynomials in one set of variables. On Pm, we have the polynomials in another set of variables. And we take zero sets of polynomials in both sets of variables, which are homogeneous in, say, the x variables, homogeneous in the y variables, but not necessarily of the same degree. Okay, so that's the statement. Yeah. Okay. Could also have maybe, I mean, now I've done it this way, but for the future, one could consider the question whether you would find it easier if one starts with that. No, obviously one could have worked, say, Pn times Pm. One looks at that as a set. The polynomials that we consider are B-homogeneous polynomials. And then we define everything in terms of that. That would also have been possible. But now we do it out. So, lemma. The closed subsets of Pn times Pm are precisely the zero sets of polynomials say it's the f, so the zero sets of polynomials as usual, f in k x0 to xn for the coordinates of n, y0 to ym, which are bihomogeneous. So that means if I fix the y variables and view them as polynomials in x0 to xn, then they are homogeneous of some degree. If I fix the x variables, as parameters, so I can view them, so let me say it differently, I can view them as polynomials in y0 to ym, whose coefficients are polynomials in x0 to xn. Then as polynomials in these variables, they are homogeneous of some degree. And also view them as polynomials in x0 to xn, whose coefficients are polynomials in y0 to ym. Then in this sense, they are homogeneous of some possibly different degree. As polynomials in x0 to xn, they are homogeneous of some degree, and as polynomials in x0 to ym, they are homogeneous of possibly a different degree, of possibly another. Okay, so let's see. I want to show this. First, I have to remind me what it means. So let W in Pn times Pn be closed. So this means that W is the inverse image under sigma of a closed subset in Pn. A, where A in P large n is closed. No, that's what it means. So thus A is a zero set of some set of homogeneous polynomials in the variables in P large n. Thus, A can be written as a zero set of, say, f1 of, say, xij, no, maybe it was zij, I from 0 to n, j from 0 to m, until some whatever, which I can do with quite many, fr from zij, I from 0 to n, j from 0 to m. Okay, it can be written as a common zero set of these polynomials in these variables on P large n. So now what is, know that the map sigma is given by sending x1 so x0 to xn, y0 to yn, to the product of all the coordinates. So it's given by xi, yj. So you can also define it as a I from 0 to n, j from 0 to m. So it's just point ai, bj is sent to this. So that means if I take the what is then the pullback of, I mean, what happens to this function? So the zero set of this thing, of Zij, becomes the zero set of xi times yj. So that means just set f1 of xi times yj, where I goes from 0 to n, j goes from 0 to n, m it was here, and so on until fr of set xi times yj, I goes from 0 n, j goes to 0 n. Now, these were, so I should have said where the fi are homogeneous polynomials. Of some degree d, of some degree di. Then you see if you just replace Zij by this, now the polynomial becomes homogeneous in the xi and in the yj, and actually both of the same degree di. So thus, now fi is bihomogeneous of degrees di. No? So in some sense we have shown that if we have a zero set, if we have some closed subset in Pn, then its inverse image is a zero set of some bihomogeneous polynomial where we even have that they have the same degree. So we have proven a little bit more than we even wanted, but anyway, but we have certainly shown it is the zero set of bihomogeneous polynomials. So this is one direction. So now we have to show that if we do have a zero set of a set of bihomogeneous polynomials, then it is closed. Now, conversely, let W be in, again, zero set of some polynomials, f1 of xi yj times yj, xi comma yj. So again, maybe now remember that I goes from 0 to n, j goes from 0 to n, maybe I don't always write it. So fr of xi yj, so where the fi are bihomogeneous in x and y, in the xi and the yj. So now the first thing that we want is that we go back to here, that we can take them bihomogeneous in the x and the y variables, but of the same degree. So here we don't assume that, so we want to change things so that they are bihomogeneous of the same degree. And so, so if, say, fi is bihomogeneous in the xi, so we just say homogeneous in the xi of degree, what I want, s, and homogeneous in the yj of degree t, then, and we can assume, for instance, that what I want with s smaller than t, obviously if it's the other way around, we could change the role of x and y, then we want to see that we can replace this polynomial by some others which have the same zero set. And then I just say that then we replace this thing fi by x0 to the t minus s fi comma x1 to the t minus s fi until x n to the t minus s fi. So instead of this one polynomial fi, we take these n plus 1 polynomials. And the point is that these have the same zero set, because these x0 to the t minus s until x1 to the t minus s and so on, the common zero set is zero, is empty, which have the same zero set. So if we do this here, we can, after replacing our polynomials here by possibly many more.
If the number of the polynomials exceeds the number of the variables.
Well, why should this matter?
Because here you for every sorry, I thought for every polynomial you are choosing a variable.
What?
I'm wrong.
Okay, but you know, I mean, just to do it, for every polynomial we do this.
Yeah.
But there's no, we have no restriction of how many, how many we can choose. I mean, at the worst, if the difference of the degrees is 100, then we get 100 times as many polynomials as before. And no, actually not. It just depends on. We don't. We just have as many as this. So it's not a big deal. In the most, we have kind of n times as many as before, n plus 1. So which have the same zero set. So in this way, thus we can assume that all the polynomials fi, so each fj is bihomogeneous in the xi and yj of the same degree. And now if you think of it, if you have a polynomial which depends on variables x0 to xn and y0 to yn, and it's bihomogeneous of the same degree, so that every monomial has as many x's in it, factors xi in it as factors yj, then you can write it as a polynomial in the products of some xi's by some yj's. So thus you can write fj of xi from yj as j tilde of xi times yj. So this is here, maybe I should say xi, for all possible i's, yj, for all possible j. This is also a polynomial, which I write differently, of maybe I call k then, of xi times yj, where this runs through all possibilities. No, just if you have 5 x to the 3, 1 to the 3, x2, y0 squared, y1, something like that, plus other terms. So you just can, there are many ways how you can do it, but you can just write this. This is 5 times x1, what do I want? x1 y0 squared times x1 of the same degree. X1 y1 times x2, y0. So you can just group them together. You just can pair off the x variable to the y variable, so it becomes a polynomial in products. Okay. But so that means you have a polynomial like this, and so therefore it is the inverse image of that. Thus, we have that W is equal to 0 set f1 tilde of xi times yj, f whatever it was, r tilde of xi times yj, which is the inverse image of f1 tilde of zij. No? So where here again, I and j run. No? I think it's clear. Okay. Now precisely. So I have 5 minutes. Let me just give one example of this. So I claim that the diagonal in the product is always closed. So x and y are the projected, no, x is for the projected. And it follows that delta x in x times x is closed. So just make the definition. So let x be right in x directed. And obviously delta x is just the diagonal. So this is the set of all points P. P is in x in the product. PP. So it's the same point. And we also have the diagonal morphism. This is delta from x, so x times x, which just send the point P, so P times P. And then the claim is that, and obviously with image delta. And so the lemma delta x in x times x is closed, and if I take the map delta now as a map from x to delta x is an isomorphism. Okay, let me just show that it's closed. So that it's closed in the product means, the product lies in Pn times Pn. So we have to, it's therefore enough to show that P delta of Pn in Pn times Pn is closed. Because so you have delta of, so if x is in Pn, then delta x is equal to x times x intersected delta Pn. No? I mean, that's clear. So that's enough to show that delta Pn inside Pn times Pn is closed. Took a bit longer than I thought. Anyway, okay, so let's see that. And so I just write down the equation. So I claim delta Pn is equal to the zero set of the following set of equations. I just take all xi times yj minus xj times yi for I, j going from 0 to I. That would make it closed because it's a zero set of some polynomials. So why is this the case? So, if I have a point a0 to an, b0 to bn lies in this zero set, if and only if, what is it? AI times bj minus bj times ai is equal to 0 for all I and j. That is if and only
It
if.
should be bi. You just repeat it, but
Yeah. Okay. Yeah. No, otherwise it would be a bit too easy. And so this is the same as saying that if I take the matrix B0 to an, B0 to Bn, that this matrix, these are points in projective space, so this thing is not 0, this thing is not 0, this is if and only if the rank of this matrix is 1. Because these are precisely all the ranks of the 2 by 2 subdeterminants. And so this is if and only if this one as a point in projective space. And so this means, in fact, that this was correct and this is a closed subset. And the fact that this is an isomorphism is kind of trivial because obviously it's a morphism. We have seen this before because it's given by pair morphisms like that. So here is delta x to delta x is a morphism. Check its inverse. Well, it will be just a projection to one factor, whichever you want. No? PP. Okay, so sorry for going over time. So maybe that's enough now. So maybe, well, I will repeat it again next time because it's important, but I say it once. So now, so this thing that the diagonal is closed is actually quite important because this is the property that all quasi-projective, so that means affine or projective varieties, have, which replaces for us the Hausdorff property. So somehow it means that for many things, obviously these varieties are never Hausdorff, the topology is terrible. But somehow the fact that the diagonal is closed sometimes allows us to work as if we would have the Hausdorff property. Because if we would have the product, if we would have defined the topology as a product just to be the product topology, then that diagonal is closed would actually be equivalent to the Hausdorff property. Now, we don't have the product topology on the product, but and we don't have the Hausdorff topology, but somehow this combines, so this is still true, and somehow it replaces, in many ways, allows us to use similar arguments as if the space was housed. Obviously, in each case you have to check whether it's legal because the space is not housed. Okay, we see this again next time. Now,